Hey everybody, welcome back to chemistry. And so in this presentation, I want to talk about something called dissociation of water. So what I'll do is I'll describe what that is, and then I'll do some problems that are regarding that concept. So I have a slide here, which I'm pretty much going to talk about on the board. So imagine that we have a beaker here of extremely pure water. So let me talk about how you might get that. So what you might do is you might go to a tap of water, say at the sink, and then fill up maybe some kind of container with that water. Now the water from the tap is not very pure. Although it's mostly made up of water molecules, there are plenty of other molecules in it as well. For example, you have ions that are in there that are due to sodium chloride or potassium chloride and other ionic compounds that are dissolved in there. So the water from the tap isn't exceptionally pure, but one way you can purify that water is by distilling the water. And so what you do is you take that tap water in that container and then you boil the water. When you boil the water will vaporize off into steam while the ions and the salts will stay at the bottom of the container. And so if you collect the steam and then you condense the steam back to liquid water, then that product that you have, that liquid water after you condense it, is going to be very pure water. It's going to be almost all water molecules with very, very few other ions in it. Okay, so imagine here we have this beaker of this extremely purified distilled water. My question might be, so you have all these water molecules and you've removed all the other things that could be in the water, in particular ions that may be due to sodium chloride or potassium chloride or other ionic compounds. My question is, are there other ions in this water? And the answer, believe it or not, is yes. There are very low levels of other ions that are created by water reacting with itself. So I will talk a little bit more about the reaction in a second, but here, just to indicate here, these blue dots, again, imagine these to be water molecules, but then here, every 10 million molecules, you might have on average a pair of ions. So maybe this ion here is water plus a hydrogen ion attached to it. So that would be H3O plus, and so that is hydronium. And then this other ion here is going to be water minus a hydrogen ion, so that will be hydroxide. So again, we'll talk about how we create these in a minute. Before I do, I want to give you a sense of just how many of these hydronium hydroxide ions we have. So in the past, I've said that you will get them, say, maybe once or twice every 10 million molecules. But now I kind of want to put this in terms of concentration. So what I want to do is I want to compare the concentration of the water here in this beaker of water, which you could imagine is very high, and then compare it to the concentrations of these ions here. And so you can actually do a calculation to figure out what the concentration of the water molecules are in this beaker. So we're going to be thinking about this in terms of molarity. So you might ask yourself, well, are these water molecules at their like 1.2 molar concentration or 5.3 molar? What is the concentration of water molecules, say, in a beaker of water? So you can work that out by calculation. So let me show you how you do that. What you're going to do is you'll take the density of water here, which is 1 gram per milliliter. And then what we're going to do is we're going to do some dimensional analysis. So first thing I want to do is I want to convert milliliters to liters. And so to do that, I'm wanting the milliliters to cancel out. So I'll have 1 milliliter in the numerator here. And then you might recall that 1 milliliter has a thousandth of a liter. And I'll put that in the denominator here. So it's 1 times 10 to the negative 3 liters. And so right now, what you can see is that milliliters would cancel out. And right now, if you were to do the math, you would have a value in grams per liter. So what I want to do now is I want to get here grams per liter into moles per liter, because moles per liter is molarity. And so we want a relationship between the grams and moles of water. And so you know what that is. That will be the molar mass of water. So we know that 1 mole of water has a mass of 18.02 grams. You can figure that out from the periodic table. So here, what I'm going to do is I'm going to have another fraction here. So what we have is 1 mole in the numerator, and we have 18.02 grams of water in the denominator. And so if you were to do this math, which would be what? 1 times 1 times 1 divided by 1. We could put a 1 from this middle here if we want. Divided by 1 times 10 to the negative 3. Divided by 18.02. The number you get is 55.5. And so what are the units here? And so you can see the grams cancels out. So we're left with units of mole here and liter in the denominator. So this is mole per liter. And so here the concentration of pure water is 55.5 molar. So what I'm going to do is I'm going to quickly erase this here and indicate here that our concentration in this beaker of water of the water molecules themselves is 55.5 molar. Now, there's really no way you can sort of by calculation figure out what the concentrations of these ions are. But we have carefully measured the ion concentrations, and we know what the values are in molar, and they are very, very small numbers. So hydronium here, its concentration is a very small number. It's 1 times 10 to the negative 7 molar. So we're going to write this as a decimal. 0.12345 molar. So that would be 1 times 10 to the negative 7 molar of hydronium. And then hydroxide in this water here has the same concentration. Okay, so again, I'm writing out these decimals so you can just see how unconcentrated these ions are compared to the 55.5 molar water. Okay, so we have measured these values for the concentration of the ions. And so you might wonder where those ions come from. So you may already know this, and that what happens, one of about every 10 million molecules, is that one water molecule will react with another water molecule. So let me describe that reaction. So we have water here, and it reacts with another water molecule. And so you might remember how I told you this happened before, in that here from this water, one of the hydrogens in the form of a hydrogen ion will break off this water and stick onto the other water, right? So imagine what you get when that happens. Well, here, this water loses a hydrogen ion, so it becomes OH minus, which you guys know is hydroxide. And then that hydrogen ion travels to this water picks up the hydrogen ion, and it becomes H3O plus, which is hydronium. Now, one thing you should be aware of, and I think you probably already know, it's not the case where you have all of these water molecules converting to hydroxide and hydronium. That doesn't happen. So when you see this reaction, you just have to remind yourself that it's not every single of these water molecules is reacting with itself to form hydroxide and hydronium. In fact, this rarely happens. And to remind ourselves that this is a reaction that doesn't happen very often, we write here the reverse arrows. Now, this tells us that here we have an equilibrium between the numbers of the water molecules and the numbers of hydroxide and hydronium. And so you can see that the water reactant molecules are at about 55.5 molar, while these ions here are each at about 1 times 10 to the negative 7 molar. So what that tells you is when this equilibrium is achieved, which occurs in just all the time in ordinary water, you're going to have far more water molecules than you have of hydronium hydroxide. And so to remind ourselves of that, what we can do is we can draw the arrows such that they tell us here that here this is an equilibrium which is greatly shifted to the left. It's greatly shifted to the reactants. Okay, sounds good. All right, now what chemists often do is they're often pretty bored with a beaker of water, right? There's nothing really too exciting going on in a beaker of water. However, what chemists like to do is they might like to add additional hydronium into this water and then see what happens to the hydroxide. Or they might add additional hydroxide to the water and see what happens to the hydronium. And the nice thing about this is chemists know is that the concentration of hydronium is very much related to the concentration of hydroxide in water. And so if you know one, you can figure out the other pretty easily. So let me show you how you do that. So let me describe the relationship between the concentration of hydronium and the concentration of hydroxide. So you represent the concentration of hydronium by writing the formula for hydronium, and then the brackets remind us is that we're going to be considering this as a molar concentration. If you multiply that by the molar concentration of hydroxide, the value we'll always get is 1 times 10 to the negative 14. And so most chemistry textbooks will indicate a unit here, a molar squared, but yours does not, and so I don't think it's really that important to know the unit there, but you do need to have this relationship memorized, that the concentration of hydronium times the concentration of hydroxide is 1 times 10 to the negative 14. Okay, so now what I want to do is write a few equations that I think you should know for the test or for your homework. So one I just gave to you is the molar concentration of hydronium times the molar concentration of hydroxide is equal to 1 times 10 to the negative 14. Okay, so now let's say you have a problem where you know the hydronium concentration and you're trying to figure out hydroxide. And so you would solve this equation for hydroxide. So I'm going to write OH minus. Hydroxide is equal to 1 times 10 to the negative 14 divided by the hydronium concentration. Okay, so let's go ahead and solve a problem using this equation. So if I can increase the slide just for a second. So the problem reads as follows. If the concentration of hydronium of a solution is 1 times 10 to the negative 3 molar, what is the concentration of hydroxide? And then they're asking, is the solution acidic or basic? And then why is it when the hydronium is high, hydroxide is low? So if I can decrease the slide. Okay, so let's address the first question here. If the concentration of hydronium is that value, which is 1 times 10 to the negative 3 molar, what is the concentration of hydroxide? And so you would use that equation, which I just presented, which is hydroxide is 1 times 10 to the negative 14. Again, you can probably leave out the units if you want here. And then you divide it by the hydronium concentration. And so that's going to be equal to 1 times 10 to the negative 14. And the hydronium concentration is 1 times 10 to the negative 3. Again, you can probably go ahead and leave out the molar units here. Just make sure when you use these equations that the concentrations you use are in molar. Okay, so here, to find the hydroxide, you would just put 1 times 10 to the negative 14 in your calculator and divide it by 1 times 10 to the negative 3. And so the hydroxide here is going to be 1 times 10 to the negative 11. All right. So we just worked that out here. So let me just erase this really quickly. And then what I want to do is kind of remind you what the hydronium was. And the problem tells us what it was. The hydronium is 1 times 10 to the negative 3. And I'll include units here if I want. That's fine. Okay. So now you have to figure out whether this solution is acidic or basic. So what I would like to do now is go over how do you figure out from the hydronium concentration whether you have a neutral solution, acidic solution, or basic solution. So if I can increase the slide. So this slide sort of summarizes how you can determine what kind of solution you have. And so what you really have to pay attention to is the hydronium concentration here. And if your hydronium concentration is this value, which is times 10 to the negative 7, and so I've been kind of writing it as 1 times 10 to the negative 7. If the hydronium is that value here, then you have a neutral solution. And also, just as a side note, I think you know if the hydronium is 1 times 10 to the negative 7, then the hydroxide is going to be 1 times 10 to the negative 7. But oftentimes, you will not have a solution with hydronium that's exactly 1 times 10 to the negative 7, like with this particular problem here. With this particular problem, we have a value that is greater than 1 times 10 to the negative 7. And so if you have a solution whose hydronium is greater than 1 times 10 to the negative 7, then this is an acidic solution. And also, one of the things you may have noticed is that if you have a concentration of hydronium that's greater than 1 times 10 to the negative 7, let's say it's something like 1 times 10 to the negative 5, or 1 times 10 to the negative 4, or 1 times 10 to the negative 3, if that is the case, then the hydronium will be greater than the hydroxide concentration. So with an acidic solution where the hydronium is 1 times 10 to the negative 7, it will turn out that hydronium will be greater than the hydroxide. And last but not least, you may have a solution where you have a hydronium concentration which is less than 1 times 10 to the negative 7 molar. And so it may be like 1 times 10 to the negative 9, or 1 times 10 to the negative 10, or 1 times 10 to the negative 11, something like that. So when you have a hydronium that is less than 1 times 10 to the negative 7 molar, this is a basic solution. And so in basic solutions, you may have seen that hydronium here is going to be less than the hydroxide concentration. So what I want to do is I want to use this information to go ahead and solve the problem. So if I can decrease the slide. If you want to determine whether a solution is acidic or basic, probably the easiest thing to do is look at the hydronium concentration. If the hydronium concentration is exactly 1 times 10 to the negative 7 molar, it is neutral. If the hydronium concentration is a larger number than 1 times 10 to the negative 7 molar, it is acidic. If you have a hydronium concentration that is less than 1 times 10 to the negative 7 molar, it is basic. So what I'm hoping you can sort of see is 1 times 10 to the negative 3 molar, this is a larger number than 1 times 10 to the negative 7. So really quickly, what is 1 times 10 to the negative 3? It's 0.001, right? What is 1 times 10 to the negative 7? So 0.00. Okay, so this would be 1 times 10 to the negative 7 molar. So I think you can see that 1 times 10 to the negative 7 molar is a very small number. And in fact, 1 times 10 to the negative 3 is a slightly larger number. So if that's the case, if you have a hydronium concentration which is greater than 1 times 10 to the negative 7, then this is considered an acidic solution. So this is acidic. Okay. So now the $28 million question, which is this. Why is it that the hydroxide concentration is not the same as hydronium? That's maybe what you might expect, right? But what you can see is that the hydronium concentration is relatively high, and for some reason, that pushes the hydroxide concentration to be on the low side. Now, one way you can think about it is the reason why hydroxide has to go low while hydronium goes high is because when you multiply these numbers, you have to get 1 times 10 to the negative 14. But here is another way to think about it. You want to think about it maybe in terms of Le-Chatelier's principle. So here we have water reacting with water, and we have an equilibrium here producing hydronium and hydroxide. So imagine here you are at equilibrium, and so you know what the concentrations of the ions will be at equilibrium. So let me just write that here. It's 1 times 10 to the negative 7, and then hydroxide is also 1 times 10 to the negative 7. So when you have neutral water with nothing else added at equilibrium, concentration of hydronium is 1 times 10 to the negative 7, concentration of hydroxide is the same value. Okay, now here in this problem, what the chemists did is they added a fair amount of acid here to the solution. So here, the acid concentration actually went up, okay? So it went from 1 times 10 to the negative 7 up to 1 times 10 to the negative 3. So let's think about how this equilibrium will respond. So we're greatly, really considerably increasing the concentration of hydronium. So by Le Chatelier's principle, you know that if you're increasing the hydronium concentration by increasing it to 1 times 10 to the negative 3, the equilibrium will respond to somehow take that hydronium away. So how do you do that? Do you increase the forward reaction or do you increase the reverse reaction? And I think you can see is here to take hydronium away, you really need to increase here this reverse reaction. So imagine what happens when you increase the reverse reaction. What will happen is the hydroxide was at 1 times 10 to the negative 7, but when you increase the reverse reaction, the hydroxide will be taken away and it will turn into water. So when you throw in 1 times 10 to the negative 3 hydronium, hydroxide will fall because it's being taken away and turned to water, and it falls all the way down to 1 times 10 to the negative 11 molar. Okay, so that's why that happens. And so if I can increase the slide.